Section 4.4, converting other bases to base 10. In this section, we're going to talk about how there are other bases that are used throughout the world. And we're going to talk about how to convert those number-based systems into base 10. Let me share my screen here. So the title of the section is Converting Other Bases to Base 10. We talked in a different section about how the ancient Babylonian used to have a base 60 number system. But there have been many different cultures throughout history that have used many different bases for their number system. Remember, the one that we use, the one that almost everyone in the world uses right now, is called the Hindu-Arabic number system, and that is a base 10 number system. So base 10 is a very popular one. You can see here many cultures throughout history have used different looking base 10 number systems. But that is not the only one. You can see that there are a couple of cultures. These are in many cases very ancient cultures. A lot of these, I'm sure you've never even heard of these words. These are very ancient cultures, and most of these number systems have died off by now. But I'm showing you the culture and what base their number system was in. So there's a couple of cultures there that used actually a base 4 number system. There have been cultures that have used base 5 number system, base 6 number system. Base 10 has been a very popular one. We see base 11, base 12, base 15, base 20. The Mayan Indians actually had a very popular number system that was basically a base 20 number system. We believe they chose base 20 because we believe the Mayan Indians counted not only on their fingers, but also on their toes. We believe that we use a base 10 number system because 10 sort of makes sense to us because we have 10 fingers. And so when we count, we count to 10. But we believe the Mayans counted not only on their fingers, but also on their toes. So they had 20. So we believe that's why the Mayan Indians chose base 20 as their number system. So 20 was a pretty popular one. A couple cultures used base 23, base 24, base 27, and then a few cultures used base 60 like the Babylonians did. So I think this is just kind of an interesting historical table showing you that there have been a lot of different bases used in different cultures' number systems. So in this section, we start to consider other bases besides base 10. We're not going to use different symbols like last section. We talked about the Babylonians and we had to learn new symbols. So we're not going to necessarily learn new symbols, although we do something weird a little bit with letters as numbers. But besides that, we basically use the same symbols that we're used to. We just talk about different bases, like what if we weren't using base 10? What if we were using base 2 or base 8 or base 16? So base 10, of course, is the main one. That's the one that we know, called the decimal system or the Hindu-Arabic number system. But binary means base 2. So binary is the name of the base 2 number system. And that's used a lot in computers. Octal is the name of the base 8 number system, and that's used to shorten long binary numbers. And then hexadecimal is the name of base 16 number system, and that is also used in computers. So if you're going to go into a career in computers or computer programming or something like that, you may want to pay attention to this lecture today, especially when we talk about base 2 or base 8 or base 16. So those are the three most like popular ones that are used even today, and often mostly in computer programming. To differentiate between bases, we will label each non-base 10 number with a subscript that indicates the base. For example, 2314 base 5 is going to represent a base 5 number. If a number is written without a subscript, it's understood to be base 10. So here's how we're going to convert a non-base 10 number into a base 10 number. So if we're trying to start with 2314 base 5, we start with 2314 base 5. If you remember from what we spoke about in the last section about the Babylonians and about our number system and how base 10 compares to base 60, the number on the far right is always the ones place, right? And as far as we're concerned, usually that is considered the ones place because 10 to the 0 is 1. And then the next one over is usually called the tens place, at least in base 10, and that's because 10 to the first power is 10. The next one over would be called the hundreds place because 10 to the second power is 100, and then the next one over is the thousands place because 10 to the third power is 1,000. But that's if we're talking about base 10. If we were talking about base 5, these would all represent place values that are powers of 5. In other words, this 4 right here on the far right would be still in the ones place, but that's because 5 to the power of 0 equals 1. The next digit over would now be the fives place because 5 to the first power is 5. The next digit over would be the 25s place because 5 to the second power is 25. And then the next digit over would be the 125s place, and that's because 5 to the third power is 125. So on the far right is always to the 0 power, and then next to that it's to the first power, and then the second power and third power, and so on if we were to go further to the left. So this 2 right here represents two sets of 5 to the third. This 3 right here represents 3 sets of 5 squared. This 1 right here represents 1 set of 5 to the first power, and then this 4 on the far right represents 4 sets of 5 to the 0. Again, we're using fives because it says base 5. That subscript after the 2314 is base 5. Normally, we would put tens in place of all those fives, but not when we're doing base 5. So 5 to the third is 125, 5 to the second is 25, 5 to the first is 5, and 5 to the 0 is 1. So that represents 2 sets of 125, which is 250, plus 3 sets of 25, which is 75, plus 1 set of 5, which is 5, and finally 4 sets of 1, which is 4. If you add all those up, you get 334. So we can say that 2314 base 5 equals 334. So that's my final answer right there. 2314 base 5, when I convert that into base 10, it is equal to 334. I want to point out that I'm saying 2314 base 5. I'm not saying 2314 base 5. And I'm doing that on purpose because when I say 2314, your mind thinks base 10, right? What we normally would think of as 2314. But this is not that, right? So I don't want to say 2314 because that 2 is not in the thousands place, right? And so I'm going to try to stay away from that. I want to say 2314 base 5 equals 334. Okay. So we're going to notice that in different bases, we're only allowed to use certain digits. For example, in base 10, we have 10 digits allowed. Like all of our numbers are made up of these 10 digits, which are 0 through 9. In base 5, we just did an example of base 5. We only have these 5 digits allowed. 0 through 4. Those are the only 5 digits that have to make up all of our numbers in the base 5 number system. You can see in base 2, there's only 2 digits allowed. In base 2, everything is made up of ones and zeros only. So this is a helpful table. We'll probably refer to this table, as we go today. Things get even more strange once we get past base 10. For example, in base 11, what we would think of as 10 is not a double-digit number because your first double-digit number in base 11 doesn't happen until you hit 11. And so we need 10 to be represented as a single-digit number. And we usually use letters in that case. And so once you see anything past base 10, you occasionally might see letters show up in your numbers. And that's weird, but every time you see that, when they write an A, that's equal to what we think of as 10. When they write a B, that's equal to what we think of as 11, and so on. So this is a helpful table right here, and I'll probably show this a couple times throughout the day. But when we do see letters in our numbers, which could happen for bases anything bigger than 10, that's what those letters stand for. And by the way, in this class, we are only going to be responsible up to base 16. I will not ask you anything past base 16. So in this class, we are responsible for everything from base 2 all the way up through base 16. Here's another example. Here's the base 12 example. B37 base 12. Let's try to translate or convert B37 base 12 into base 10. What would that equal in the base 10 number system? So remember, the far right number is always your ones place. This time it's the ones place because 12 to the power of 0 equals 1. So that 7 that you're looking at on the far right is representing 7 sets of 12 to the 0 power, which is 7 sets of 1. That 3 that you're looking at right in the middle there, that represents 3 sets of 12 to the first power, because we're doing base 12. We're not doing base 10 right now, we're doing base 12. So we're going up by powers of 12 here. So that 3 in the middle represents 3 sets of 12 to the first power. That B right there, that B is actually, remember, representing 11. When we're doing base 12, all of the numbers are made up of these types of characters right here. And the A equals 10 and the B equals 11. And so B equals 11. So when we see that B right there, that represents 11 sets of 12 to the second power. That's what that means. So that's 11 sets of 144, which is 1,584. That's 3 sets of 12, which is 36. And that's 7 sets of 1, which is 7. If you add those numbers up, you get 1627. And so my final answer is that B37 base 12 is equal to what we would call 1,627. In some alternate universe, if they would have chosen base 12 as their base for the number system instead of base 10, the number that they would write as B37 would be equivalent to what we would think of as 1,627 in our base 10 number system. So notice I didn't write a base right here. Remember, we said earlier, when you don't write a subscript, it's assumed to be base 10. It's assumed to be our normal base 10 Hindu Arabic number system. Here's another example we could go through. I think I'll just show you this example. I think you can just read through this example on your own, and you can see if we're doing base 8, all of these go by powers of 8, starting with 8 to the 0 on the far right, and then going up powers of 8 to the left. 8 to the 0, 8 to the first, 8 to the second. You can just go through the math on this, and you can see how 614 base 8 should be equal to 396. If you need to, go ahead and pause the video and kind of look at this a little closer, but you will see that 614 base 8 equals to what we would call 396. Here is another example in base 2. Remember, in base 2, you're only allowed to use zeros and ones. All of the numbers will be made up of zeros and ones. So sometimes you get a really long string of zeros and ones, but it doesn't really equal a number that's that big, because this is actually a 6-digit number in base 2, but it's only equal to 54. It's only equal to a 2-digit number in base 10. So if you would like to, if you need to, pause your video and kind of look closer at what we are looking at here, that would be a good idea. Otherwise, I'm not going to say too much about it. You can kind of go through and see how this works. But 110110 base 2 turns out to equal to 54 in base 10. Here's another example, base 16. I gave you an example here with a couple of letters in it. An F and a C, kind of going back up. Remember, when you see letters, this is kind of a good table to help you remember what they're equal to. Also, when you're doing base 16, you have 16 characters, because we need 16 characters because that means there are 16 numbers that are supposed to be single-digit numbers, and that's actually 0 up through 15. The first double-digit number in base 16 is not going to be until we hit the number 16, what we would call 16. That's going to be the first double-digit number. So everything before 16, including 0, has to be a single-digit number. That's why we have to use all these letters sometimes. So if we're doing base 16, we're going to use this, and you can kind of see how this works. So F2C5 base 16 is equivalent to what we would call 62,149. Again, pause the video if you need to and kind of look closer and see the patterns and see how this all works and see why this problem works out the way that it does. Let me go ahead and stop the screen share, and we will now do some examples on our paper. So I have this table, same table that we just saw, so I'll kind of maybe come back and forth, show you this once in a while. But this is the same table we just saw. I don't think I need to talk about this too much. It's what we just saw on the screen share. There's also something that we just saw on the screen share. Once we get past base 10, we sometimes start using letters. So we saw that on the screen share also. I don't think I need to talk about that too much. And then the next page, same thing. It's just repeating what we just saw on our screen share. Talking about how letters show up occasionally once we get past base 10, and specifically telling you what those letters are representing once we get past base 10. So we kind of already talked about that, but I may kind of pull those up as we go. All right. Let's go ahead and get to our examples. We have several examples where we are going to try to convert different bases into base 10. So in these first three here, we're We're looking at base 2 numbers, and we're trying to convert base 2 numbers into base 10. You saw several examples already on the screen share. You may be at a point where you can just try these already. You may want to pause the video right now and try these 3 problems and see how you do. If you don't feel ready for that, that's fine. Just keep watching. Let's go ahead and talk about how this would work. So this is base 2. I know it's base 2 because it says it right there. The far right is the 2 to the zeros position, and the next one is the 2 to the first powers position, and so on. So this is saying I have 0 sets of 2 to the 0 power, and I have 1 set 2 to the first power. That is telling me how many 2 to the 0 powers I have, and that is telling me how many 2 to the first powers I have. 2 to the 0, of course, is equal to 1. Remember, anything to the 0 is equal to 1. 2 to the first power is equal to 2. This is simply saying I have 1 set of 2 plus 0 sets of 1. It is saying I have 1 set of 2 plus 0 sets of 1, which is, of course, 2 plus 0, which is, of course, 2. We're not always going to write it out that detailed every single problem. We're going to do several of these today. But for the first, beginning problems, I might. 1, 0 base 2 is equal to what we would call 2 in base 10. So the way we would write what we think of as 2 in base 2 would actually be 1, 0. I know that looks like 10, but don't call that 10 because that's not what we would think of as, that's not 10 to us. So I'm going to say 1, 0 base 2 is equal to 2 in the base 10 number system. So what about the next one? Remember, the far right is telling you, in this case, 2 to the 0 powers space. And then the next one is the 2 to the first power space. And then the next one is the 2 to the second power space. 2 to the 0, of course, is 1. 2 to the first power is 2. 2 times 2 is 4. This is saying I have 1 set of 4 plus 1 set of 2 plus 1 set of 1. I have 1 set of 2 squared. I have 1 set of 2 to the first power. I have 1 set of 2 to the 0 power. That means I have 1 set of 4. 2 times 2 is 4. 1 set of 2. 1 set of 1. Of course, that means I have 4 plus 2 plus 1, which we would call 7. So in our world, the number 7, we would call 7. If we wanted to translate that into base 2 number system, it would be written as 111. Do not say 111. That is not the hundredth place. Do not say 111. We're going to say 111 base 2. In some alternate universe, if base 2 would have been chosen as our base instead of base 10, the number that we currently think of as 7 would be instead written like that. Okay, for the last base 2 example, this is a really long one. I think I'm not going to show as much work, obviously, it's really long. But remember, this on the far right, so we're using powers of 2 in this case. It's always the 0 power, and then the first power, and then the second power, and so on. This is going to be how many 2 to the 0 powers I have, how many 2 to the first powers I have, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. So this one way over here is saying that I have 1 set of 2 to the seventh. Right next to it is saying that I have 1 set of 2 to the sixth power. Right next to that is saying I have 0 sets of 2 to the 5th. And then I have 1 set of 2 to the 4th. Let's see if I could squeeze all these in. I have 0 sets of 2 to the 3rd. I have 1 set of 2 to the 2nd, and I'm not going to squeeze them all in. I have 1 set of 2 to the 1st. And then finally, I have 0 sets of 2 to the 0. Okay, so I know this is 8 digits, 1, 2, 3, 4, 5, 6, 7, 8, but that doesn't mean you start at 8 there, because the one on the far right is always the 0 power. Okay, so if you see 8 digits, we actually start with the 7th power. You see 3 digits, we start with the 2nd power. And that's because the one on the far right is always representing your 0 power. So that represents the 0 power, that represents the 1st power, that represents the 2nd power, and so on, all the way till that representing the 7th power. I'm just going to go ahead and skip a little bit because 2 to the 7th is 128 times 1. 2 to the 6th is 64 times 1. This is 32 times 0. This is 16 times 1. 8 times 0. 4 times 1. 2 times 1. 1 times 0. Then we just go ahead and add all those numbers up. We should get 214. So 214 is a 3-digit number in the number system that we're used to, but it's actually an 8-digit number in base 2. Base 2 numbers can get really long. It's an 8-digit number, but it only represents 214. Okay, let's move on to the next set of examples. Converting some numbers into base 10, but now we are looking at some base 6 numbers. In base 6 number system, we only are allowed to use these characters 0 through 5. You will notice that all of these only have 0s through 5s. They don't have anything else. And that's because once you hit base 6, once you hit the number that we think of as 6, it actually is a 2-digit number already. So these are the only single-digit numbers. 0 through 5 are the only single-digit numbers in base 6. That's why you only see 0 through 5s. You will never see the character 6 or 7 or 8 or 9. You will never see those characters show up in base 6. It's because those are double-digit numbers in base 6. So now we're talking base 6. So now these go up by powers of 6. This is my 6 to the 0's position. This is my 6 to the 1st power's position, and so on. This is saying I have 1 set of 6 to the 1st plus 0 sets of 6 to the 0. This means I have 1 set of 6 plus 0 sets of 1, which just means, of course, 6 plus 0 or 6. So remember I said in base 6 number system, 6 is going to be a 2-digit number. The thing that we think of as 6 is going to be a 2-digit number, and it actually is 1, 0. It looks like 10, but don't call that 10. It's not, we're in base 6. So we say 1, 0 base 6, but 1, 0 base 6 is equal to what we call 6. Now that kind of happened right here also. Remember that 1, 0 base 2 is equal to what we call 2. 1, 0 base 6 is equal to what we call 6. That's going to happen every time. If you look at 1, 0, then whatever the base is going to be your answer over here. If you're looking at 1, 0, whatever the base is going to be your answer over here every single time. Okay, what about 1, 3, 2 base 6? This is my 6 to the zeros position, which is the ones place. This is my 6 to the first powers position, which is the sixes place. Now this is representing how many 6 to the second powers I have, or how many sets of 36 I have. This means I have one set of 6 squared plus 3 sets of 6 to the power of 1 plus 2 sets of 6 to the power of 0. This means I have one set of 36 plus 3 sets of 6 plus 2 sets of 1. Again, I'm not going to always show as much work as I am in the beginning here. As we get to the next couple pages, I'll probably go a little faster. But this is 36 plus 18 plus 2, which is equal to what we would think of as 56. Again, I don't need to put a base here because it's assumed base 10 when we leave the base blank. It's assumed we're talking base 10. So 132 base 6 is equal to what we call 56. Okay, let me go a little faster on this one. So we have our 6 to the zeros place, 6 to the first powers place, 6 to the second. Now we're going 6 to the third powers place. We have 5 sets of 6 to the third. We have 0 sets of 6 to the second, 1 set of 6 to the first, and 2 sets of 6 to the 0. Well, 6 to the third means 6 times 6 times 6. That means I have 5 sets of 216. I have 0 sets of 36, 1 set of 6, and 2 sets of 1. Go ahead and do the math. 5 times 216 is 1080. 0, 6, 2, 1088 should be the final answer here. Okay, let's go ahead and move on. I'm just picking some random bases here. Remember, you are responsible for everything from base 2 up to base 16 in this class. Here's some base 8 problems. I really think most of you probably understand it by now. So it's very possible you could pause the video and try these. Let me work on trying to get this better in focus here. You could probably pause the video and try these and probably do well. Remember what I just told you about when it says 1, 0. We had talked about when it says 1, 0, 1, 0 base 2 happens to equal to 2. Remember 1, 0 base 6 happened to equal to 6. I bet you can guess what 1, 0 base 8 is going to equal to. Also, if we're looking at base 8, all of the numbers are going to be made up of these characters 0 through 7. Those are the only characters we're allowed to use in base 8 are the characters 0 through 7. And that's because everything past 7 is no longer a single digit number. So it's not going to be a surprise, I hope, when this answer turns out to be 8. That 1 is telling me how many 8 to the first powers I have. That 0 is telling me how many 8 to the 0 powers I have. This is simply 1 times 8 plus 0 times 1. Okay, so that shouldn't be a surprise based on the pattern we've seen on the last couple examples. This is telling me how many 8 to the zeros. This is telling me how many 8 to the first powers, and then how many 8 to the second powers. This is saying I have 2 sets of 8 squared, 0 sets of 8 to the first, and 4 sets of 8 to the 0. Okay, so this means I have 2 sets of 64. 8 times 8 is 64. 0 sets of 8, and 4 sets of 1. That is 128 plus 0 plus 4. So 204 in the base 8 world would be equal to what we call 132. If in some alternate universe, whoever created the number system had decided that they wanted to use base 8 instead of base 10, then the number that we currently think of as 132 would have been written as 204 instead. And that sounds strange. You think, what? That's crazy. Why would they use base 8? Well, why did they use base 10? They didn't have to use base 10. We don't have to use base 10. It just seems normal to us because that's what we've done all our lives, and that's what people have done for hundreds, kind of almost thousands of years. But it was kind of arbitrary. Like there's no reason it had to be base 10. It easily could have been base 8 that became the popular one, or base 12, or base 20, or you saw all those different bases that were used throughout history. Base 10 just happens to be the one we're using right now, right? Some of those other ones were used longer than what we're using right now. So it very well could happen, in the future ahead of us in the next, hundreds or thousands of years, that maybe a different base becomes the popular one and everything changes and maybe base 10 isn't used anymore. It's not going to happen in our lifetime, of course. I highly doubt, but possible. Okay, next example for base 8. Um, 8. I'm going to go a little faster on this one. I think you guys get it by now. 8 to the 0 position, 8 to the first power, 8 to the second, 8 to the third, 8 to the fourth. So this is saying we have 7 sets of 8 to the fourth plus 6 sets of 8 to the third plus 0 sets of 8 to the second, 3 sets of 8 to the first, and 0 sets of 8 to the 0. And no, I'm not showing all this work, but the far right is always the to the zeros power, and it's the base 8 this time. So this is the 8 to the zeros position, 8 to the first powers position, 8 to the second, 8 to the third, 8 to the fourth. So I started with 7 times 8 to the fourth. Remember, there are 5 digits here, but that doesn't mean we use 5. Okay, we actually, if there's 5 digits, we always start with fourth power. That's because we have to use 0 power for our last one. I'm just going to go ahead and tell you what happens. You can figure out 8 to the fourth power and multiply it by 7. You will get 28,672. You can figure out 8 to the third power and then multiply that by 6. You will get 3072. Make sure you're doing 8 to the third first before you times by 6. Don't go 6 times 8 and then the third power. That's not how this works. The powers come before multiply in the order of operation. Exponents come before multiply in PEMDAS. So you need to do 8 to the third first and then times that answer by 6. Okay. This is, of course, going to be 0. This is simply 3 times 8. And then this is 0 times 1. 31,768. What we currently call 31,768 in base 8 land would be referred to as 76030. But they would be equivalent to each other. Base 10, base 8. Here's some base 13 examples. In base 13, all of your numbers will be made up of these digits. These are all the single digit characters we are allowed to use in base 13. Remember, A is 10, B is 11, C is 12. Okay. A is always 10. You go up from there. But if we're talking base 13, which we are on this page, these are the characters we are allowed to use right here. In base 13, we only use A, B, C, so we will not be using D, E, F. But in base 13, when you see an A, it will be 10. When you see a B, it will be 11. When you see a C, it will be 12. And then 13 would be the first double-digit number in base 13. Okay. You could probably just try to do these on your own. You could go ahead and watch. I'm going to go a little faster. I think you get the picture by now. This is 8 times 13 to the first power plus 2 times 13 to the 0 power equals 8 times 13 is 104. 2 times 1 is 2. This would be equal to 106. This represents 5 times 13 to the second plus B. Now, what is B equal to? Remember, B is equal to 11 times 13 to the first, and then 9 times 13 to the 0. Okay, remember, B is equal to 11. 13 squared is 169, I believe, times 5. Go ahead and go through the math on your calculator. I believe it's 845. This is 11 times 13, which is 143. And this is, of course, 9 times 1. 997. So 5B9 base 13 is equal to what we think of as 997. All right. This next one has a couple of letters in it. So when you see the C, we're going to make it be 12. When you see the A, we're going to make it equal to 10. 12, and so we are going to think of this as 12 times 13 to the third, 2 times 13 to the second, 10 times 13 to the first, and then finally 1 times 13 to the power of 0. Go ahead and do 13 to the third power and then multiply by 12. You will get 26,364. Go ahead and do 13 to the second and then multiply by 2. You will get 338. This is just 13 times 10. And this is 1 times 1. 26,833 is our answer. What we call 26,833 in base 13 land would be referred to as C2A1. Go through a few base 16 examples. Now we're in base 16. Remembering in base 16, you have a lot of characters that can be used because in base 16, all of these are single digit characters. So this is 10, 11, 12, 13, 14, 15. Even 15 is a single digit character in base 16. And that's because in base 16, the first double digit character is 16. So everything before 16 has to be single digit characters. That's why you have to use a lot of letters. That's why we're actually going to use all these possibly in base 16. Okay. So when we see 8 to base 16, that means 8 times 16 to the first power plus 2 times 16 to the 0 power. Eight times 16 is 128. 2 times 1 is 2. That is equal to what we would call 130. Remember, we actually just did an 8 to, on the last page, 8 to base 13, 8 to base 16. 8 to base 13 was equal to 106. 8 to base 16 is equal to 130. They're not the same, right? It's because they're different bases. (995) base 16 means 9 times 16 to the second plus 9 times 16 to the first plus 5 times 16 to the 0. 16 times 16 and then multiply that by 9, you should get 2304. 16 times 9, you should get 144, and then 5 times 1. And if you add those up, you get 2453, 2,453. (995) base 16 is equal to 2,453 in base 10. And then finally, for this page, E is 14. So I have 14 sets of, remember this is 16 to the 0, 1, 2, 3, 4. I have 14 sets of 16 to the fourth power. I have 6 sets of 16 to the third power. I have that many sets, 15 sets of 16 to the second power. I have that many sets, 12 sets of 16 to the first power. And then finally, we have 8 sets of 16 to the power of 0. I hope that makes sense how we're getting all of those things. Nine one seven 504. Not comma. Let me start with that. 917504 plus 24576 plus 3840 plus 192 plus 8. And then finally, that whole thing equals to 946120. $946,120 in the Hindu Arabic number system would be written in base 16 as E6FD8. And remember, some of these are currently used in computers, base 16, base 8, base 2. Those are things that are presently used in now. And so this is actually something that somebody might actually have to do on their job, is do a conversion like this, either way, one way or the other. In the next section, we're going to learn how to go reverse this process, go backwards. But in this section, we're going from other bases into base 10. But this is a real life thing. If you want a career in computers, computer programming, you may very well have to become proficient in base 2 or base 8 or base 16 or all of them. For the last page, I'm not going to go and do all of these examples, but I just said try these on your own. Try these problems on your own. In fact, I put 5 of them. Let me put it so you can see all 5 of them. Try these problems on your own. There are 5 examples. I highly suggest you just pause the video, try these 5 problems, and then I'll just write the final answer down. I'm not going to go through and write the whole process down, but I'm just going to write the final answer down. And you can see how you did, sort of a little self-check. So go ahead and pause the video, try these 5 problems, and come back and I'll write the answers down. Okay, 1022 base 3 turns out to equal what we would call 35 in base 10. 1022 base 7 turns out to equal what we would call 359 in base 10. 564 base 9 turns out to equal 463 in base 10. 564 base 12 turned out to be 796 in base 10. And finally, 2 bad or 2BAD base 14 turns out to equal 7,797 in base 10 land. So that's a good self-check. If you got all of those correct, you probably are doing great. If you missed any of those, kind of double check and see why you might have got a different answer. That is it for this section. Thank you for watching.